Hello everyone and welcome to our seminar, Practical Microwave Chemistry at Atmospheric Pressure. I'm your moderator, Michelle. Our presenter today is Michael Carney, Senior Research Scientist with CEM's Life Science Division. Michael is a key member of our R&D team and has been instrumental in developing new products and using existing products to develop new chemical methodologies. There will be a Q&A session at the end of the seminar, so please feel free to send in your questions via the question panel at any time during the presentation. Thank you for joining us today, Michael.
You're welcome. Thank you very much for the kind introduction, Michelle. I just want to make sure. Can everybody hear me well?
If you can hear Michael this morning, would you please raise your hand in the chat pane? We were having some audio difficulties earlier, and I just want to make sure everyone can hear.
Hopefully, everybody can pick me up pretty well right now.
Yes, we seem to have some hands up there. Yes. Okay. We seem to be doing really well. So take it away, Michael.
Hey, that's a plus. Well, thank you very, very much, Michelle, and thank you, everybody, for joining us today. Good morning, good evening, wherever you are in the world. And we'll be speaking today about something that's a little counterintuitive when it comes to microwave chemistry. I'm sure many of you may be familiar with microwave chemistry and think of it normally for high temperature, high pressure applications in sealed vessels, so very similar to a par bomb. However, today we will be discussing atmospheric pressure reactions, so reactions performed at reflux or at ambient or subambient temperatures. And first we'll start out with a little section we like to call Microwave 101, the foundations of microwave chemistry. We kind of want to make sure that everybody is on the same page when it comes to understanding the different facets of microwave heating so that when we move on to the chemistry portion, everybody has a comprehensive understanding. And so when people think of the benefits of microwave technology, 3 points really normally come to mind. Faster reactions, improved purity of product, and higher yields of your product. Now, these I'm sure many of you are familiar with, but what I'd like to speak about is something that kind of permits these advantages to microwave technology, and that's the disruptive characteristic of microwave heating. First of all, there's the rapid energy transfer. So instead of conductive heating, which heats from the outside of the vessel in towards the center and requires extensive stirring to homogenize temperature gradients throughout the sample, microwave energy is directly transferred to polar ionic species in your solution at a rapid rate, much faster than thermal methods. In addition, microwave heating is an instant on, instant off energy source. And what I mean by this is that when you have power running to your magnetron, you are running microwave energy into your solution. As soon as that power is cut off, you're no longer heating your solution with microwaves. Because of this, you're allowed a very, very quick ramp-up time, which is something that's advantageous when it comes to a lot of organic reactions. As you could imagine, if you have a hot plate or an oil bath running, you prep your sample, put it in solution, and you have to wait for it to ramp up very, very slowly to your reaction temperature. It'll run at temperature for some time, and then at that point, you'll have to take it out of the oil bath or off of the heating mantle and let it cool in a cork ring for as many as 20, 40 minutes in a very, very slow cool down time. In the case of microwave, you're up to your required reaction temperature in a matter of seconds or minutes. And then, once again, when it's coupled with forced air cooling, your temperature is brought back down from your reaction temperature to a room temperature at a very rapid pace. Because of this, you can kind of bypass possible byproduct formation that might happen at different temperatures associated with a slower ramp time. In addition, there's also a large amount of energy transferred into your reaction. As I said already, microwave energy is directly transmitted into your reaction solution rather than to the glass vessel on the outside or Teflon vessel that you may be using. In addition, it can be selectively directed, and this is something that is unique to microwave. As I'd mentioned, microwaves couple extremely well with polar or ionic substrates in solution. And so you can tune your reaction conditions through using different solvents, different concentrations to take advantage of these features. We'll get into this a little bit later. First, I'd like to introduce the schematic of a microwave to